Hello everyone. This week we will discuss a special type of unsaturated hydrocarbons called aromatic hydrocarbons. Aromatic hydrocarbons came to be called aromatic because the first few compounds belonging to this group that were discovered had a fragrant scent. Another defining characteristic of aromatic hydrocarbons is that most of them contain benzene rings. Benzene has a unique structure wherein the carbon-to-hydrogen ratio is 1:1. Aromatic hydrocarbons are also known as arenes. Benzene was first isolated by the English scientist Michael Faraday in 1825. Faraday isolated benzene from illuminating gas. The first scientist to synthesize benzene was the German chemist Erhard Mitscherlich, who synthesized benzene by heating benzoic acid with lime in 1834. Benzene is a flat symmetrical molecule with the molecular formula C6H6. Any of these three structures can be used to represent benzene. In benzene, each carbon-to-carbon double bond is intermediate between a single bond. The double bond electrons are free to move over the entire ring. Thus, these two structures are considered resonance structures. Here are some physical properties of aromatic hydrocarbons. Aromatic hydrocarbons are much less reactive than alkenes. Simple aromatic hydrocarbons are nonpolar, insoluble in water, volatile, and flammable. Several aromatic hydrocarbons have harmful biological effects. For example, benzene has been implicated as a cause of leukemia, and dimethyl substituted benzenes are central nervous system depressants. Not all aromatic compounds are benzene-based. In these compounds, at least one carbon atom is replaced by either oxygen, nitrogen, or sulfur. Examples of non-benzene compounds with aromatic properties are pyridine, a heterocyclic compound with a six-membered ring containing one nitrogen atom, and furan, a heterocyclic compound with a five-membered ring that includes a single oxygen atom. There are several ring compounds that may be mistaken for aromatic compounds. However, they do not have the same properties as aromatic compounds. Thus, they are non-aromatic. Naming benzene-based aromatic compounds is quite simple because they use the word benzene as the parent name. If there is only one side chain, no number is needed to indicate its position. A benzene ring with one side chain is also referred to as a monosubstituted benzene. Here are some examples of naming monosubstituted benzenes. In the first example, we have the halogen bromine attached to a benzene ring. We name this as bromobenzene. In the second example, we have an ethyl group attached to the benzene ring. This compound is called ethyl benzene. In the third example, we have a nitrate group attached to the benzene ring. This compound is named nitrobenzene. Many monosubstituted benzenes are more widely known by their common name rather than their IUPAC name. For example, this compound is called benzyl chloride. This is toluene. This is styrene. This is phenol. This is called benzaldehyde. This is benzoic acid. And this is aniline. It is best to just memorize these structures and their common name. Benzene parent chains with two substituents, also called disubstituted benzenes, can have 3 possible isomers. Remember that isomers are compounds with the same molecular formula but different structures. In the case of aromatic hydrocarbons, disubstituted benzenes have unique prefixes to indicate the positions of the 2 side chains relative to each other. We use the prefix ortho, meta, or para. In our first example, this compound is called ortho-dichlorobenzene. This one is called meta-dichlorobenzene. This one is called para-dichlorobenzene. Note the positions of the 2 substituents relative to each other. Ortho is the prefix used to indicate side chains that are adjacent to each other, which when numbered would be 1 and 2. Our example here is 1,2-dimethylbenzene or ortho-dimethylbenzene or simply O-dimethylbenzene. Meta is the prefix used to indicate the 1 and 3 positions. Our example here is 1,3-dimethylbenzene or meta-dimethylbenzene or simply M-dimethylbenzene. Para is the prefix used to indicate the 1 and 4 positions. Our example here is 1,4-dimethylbenzene or para-dimethylbenzene or simply P-dimethylbenzene. Our previous examples of disubstituted aromatic hydrocarbons had the same side chains. What if the side chains are 2 different compounds? In this case, we go back to our IUPAC system of arranging side chains alphabetically. Hence, in this example, 1-bromo-2-ethylbenzene can also be written as O-bromoethylbenzene. In our next example, 1-fluoro-3-nitrobenzene can also be written as M-fluoronitrobenzene. Finally, our third example is 1-bromo-4-iodobenzene or P-bromoiodobenzene. The benzene ring itself may be considered a substituent group attached to a larger parent compound. This can happen if benzene is not the longest carbon chain in the structure. When this happens, the name phenyl is used to indicate its substituency. For example, this compound has a benzene ring attached to an alkane. The alkane has 8 carbons, whereas benzene has only 6. Thus, the 8-carbon compound is the parent chain and benzene becomes a side chain. We then name this compound as 3-phenyl-octane. The 3 indicates the position where the phenyl group or the benzene ring is attached to the alkane. Let's practice drawing and naming monosubstituted and disubstituted aromatic hydrocarbons. In number 1, we have butylbenzene. We know that benzene is the parent name. So let's draw the structure of benzene. Butyl is a 4-carbon substituent. We can draw butyl anywhere on the benzene ring. Let's draw it here and count the number of carbons. 1, 2, 3, 4. So this is the structure for butylbenzene. Now let's go to number 2. We have a benzene-like compound with 2 substituents in positions 1 and 2. Thus, we can name this compound using the prefix ortho or simply O. This substituent is a 3-carbon alkyl group. A 3-carbon alkyl group is called propyl. This other substituent is the halogen bromo. To name this compound, we must arrange the substituent alphabetically. Thus, bromo should be written before propyl. And then we can write the parent name, which is benzene. So this compound is called ortho-bromo-propyl-benzene. Now let's go to number 3. This benzene-like structure has 2 substituents in positions 1 and 3. However, let's look more closely at the substituents. This substituent is hydroxide. Remember that when benzene is attached to a hydroxide, it has a special name called phenol. So, this structure has phenol as its parent name. Its other substituent is a methyl group. We can write this methyl group here. So, this is methyl phenol. Because the substituents are in the 1 and 3 position, we can call this as meta-methylphenol. However, we don't use methylphenol as the name for this compound. It is more commonly known as M-cresol. Now let's practice naming a compound where benzene is a substituent. To name this compound, we must first determine which is the parent chain or the longest carbon chain. We know that benzene has 6 carbons. What about this other compound that it is attached to? This compound is an alkane because it has only single bonds. Let's label the number of carbons. 1, 2, 3, 4, 5, 6, 7. This is a 7-carbon compound. A 7-carbon alkane is called heptane. Since it has more carbons than benzene, heptane is the parent chain name. Remember that when benzene is the substituent, its name changes to phenyl. The phenyl group is attached to heptane at the 4th carbon. Hence, we write it as 4-phenylheptane. We now go to a more complex group of aromatic hydrocarbons called polycyclic aromatic hydrocarbons. Polycyclic aromatic hydrocarbons, or PAHs, are substances that have 2 or more benzene-like rings joined together by a common bond. Naphthalene, known to many as mothballs, is the simplest and best known PAH. PAHs occur naturally and are present all around us. They are generated by the incomplete combustion of organic materials such as coal, oil, petrol, gas, and wood. They are released into the atmosphere during the burning of fossil fuels. They are present in the air, water, and soil. Biomass burning on agricultural soils release PAH, which can contaminate crops. The lead that is used in pencils is actually graphite, another PAH. Ordinary graphite consists of enormous 2-dimensional sheets of benzene-like rings stacked one on top of the other. There are many PAH that are more harmful than useful to humans and other living organisms. One such harmful PAH is benzopyrene, a cancer-causing compound. Benzopyrene contains 5 benzene rings joined together. Exposure to even a tiny amount is sufficient to induce a skin tumor in susceptible mice. Aromatic hydrocarbons do not undergo addition reactions like other hydrocarbons. They usually undergo a special type of substitution reaction known as an electrophilic aromatic substitution. In this reaction, a group substitutes for a hydrogen on the benzene ring. Benzene ring compounds undergo substitution reactions such as halogenation, alkylation, nitration, and sulfonation. Recall that benzene has 6 hydrogen atoms. These hydrogen atoms can undergo any of the substitution reactions. It does not matter which of these hydrogens is replaced because all are equally reactive. These hydrogens can be substituted by a halogen denoted with an X, an alkyl group denoted with an R, a nitrate group, or a sulfonyl group. In halogenation, a hydrogen atom is replaced by one of 2 halogen atoms. The displaced hydrogen reacts with the other halogen atom to produce an acid. In alkylation, an alkyl group replaces the hydrogen atom, which then reacts with chloride to form hydrogen chloride. In nitration, the H is replaced by nitrogen dioxide from nitric acid. The hydrogen reacts with hydroxide to form water. In sulfonation, hydrogen reacts with sulfur trioxide to form benzene sulfonic acid. If sulfuric acid is the reactant, water is also produced. Let's practice a substitution reaction involving an aromatic hydrocarbon. Here we have toluene undergoing halogenation. Toluene is a benzene-like compound with 1 methyl group attached instead of 1 hydrogen atom. For clarity, let's show the hydrogen atoms in methyl like so. We have 1 hydrogen atom here, 1 here, and 1 here. When toluene reacts with a fluoride ion under UV light, one of the hydrogen atoms in the methyl group is displaced by 1 fluoride atom. The displaced hydrogen reacts with the other fluoride atom. The resulting compound is a benzene-like structure with a methyl group with a fluorine atom attached and hydrogen fluoride. We can simplify this benzene-like compound by writing it as CH2F. This compound is called benzyl fluoride or fluoromethyl benzene. And that ends our lecture on aromatic hydrocarbons. In this lecture, we learned that aromatic hydrocarbons contain 6-membered benzene-like rings and are written with 3 double bonds alternating between single bonds. Monosubstituted benzenes are named using benzene as the parent name. Disubstituted benzenes use their prefixes ortho, meta, or para to indicate the positions of the substituents. Aromatic hydrocarbons undergo substitution reactions such as halogenation, nitration, and sulfonation. And that ends Module 2. The deadline for submission of Module 2 activity worksheet will be posted in Google Classroom. Instructions on how to submit the requirements are written in the module. Thank you for listening.